And welcome to the McKinney Amateur Radio Club's Amateur Extra Class Prep Program. We're in session number 9 tonight, so we're making headway. One more to go after this. I'm Bob, K5CRX. We'll be finishing up the electronics components section that we started the last time, and then we'll try to add a couple of additional things in there as well to keep it all together for us. So stay tuned with that, and we'll jump in that with both feet here just momentarily. And with that, let's go to our back to our components. Let me share my screen with you, and we'll get started. Okay, and there we are. And let's jump right into both feet. Okay, we're going straight through just the questions on this one. Of course, as usual, if you had any questions, we'd ask you to stop me, and otherwise we'll just keep right on rolling. We'll do a little bit of review from the last time. We'll just run through this quickly without a whole lot of commentary, but fill in a couple of gaps where it might be necessary. The last time, I didn't have some of the little diagrams that we have on it now. I've updated that a little bit. Hopefully that'll make it a little more easy to understand. An op-amp, operational amplifier, generally called op-amp. A little picture of one there in the lower right corner. You notice you have two inputs, an inverting and a non-inverting input. That's the plus and the minus. Op-amps normally require both a positive and a negative power supply voltage, and then, of course, the output from there. So that is basically an op-amp. What is an op-amp? A high gain, direct couple, differential amplifier with very high input impedance, very low output impedance. And you'll see two questions regarding the input and output impedance to follow. High input impedance and a low output impedance. You might tuck that away. Okay. What is the frequency response of the circuit? And this is shown there in E7-3. That was one of those pictures we didn't have last time, and I added that back in. Let me also make a comment before we talk about it. The R1 and the RF. R1 is the input resistor. RF is the feedback resistor, which feeds back a portion of the output signal back to the input. The relationship or the ratio between those two resistors determine the gain of the op-amp. And we'll have some questions where we actually calculate the gain. We'll get to that here shortly. But if we put a capacitor across RF, the feedback resistor, it would essentially tap off the high frequencies and allow the lower frequencies to pass on through. So the answer to that is, if we put a capacitor there, that would turn it into a low pass filter. All right. How can an unwanted ringing and audio instability be prevented in the op-amp audio filter? Well, you'll recall just about everything we do, if we want to preserve integrity, we lower the gain just a little bit, and that'll be the case here as well. Restrict the gain and the quality figure of that circuit. What is the gain bandwidth in an operational amplifier? Excuse me a second, I got to move that. An operational amplifier. And this is one we just have to memorize the answer. The open loop gain of the amplifier equals 1. Gain bandwidth. And the explanation. How does the gain of an ideal, now the key thing there, of course, is the word ideal. How does the gain of an ideal operational amplifier vary with frequency? Well, actually it doesn't. If it were ideal, it would not vary at all. Of course, ideal again is the key there, but the answer they're looking for, it doesn't vary. Okay, here we go. Now we're talking about the gain. Remember we said that the ratio between R1 and RF determines the gain. So we're looking here, we got an input resistor of 10 ohms, a feedback resistor of 470 ohms, and you divide the 470 by the 10 in order to get the gain factor. So that would give us 470 divided by 10 or 47 ohms. I mean, a gain of 47, excuse me. Boy, I'm getting my tongue tangled here today. All righty. And that's the little formula for figuring it. If you want to figure it, you can. If it's easier to remember, that's up to you. This is probably one that may be easier to remember, especially one of the little tricks on this one. In this case, the feedback resistor is 10K and the input resistor is 1K, a 1 to 10 rating again. We're 0.23 in, so a gain of 10 give us 2.3 volts, but you'll notice there's a plus 2.3 on answer B, a minus 2.3 on answer D. Since we're coming off the inverting input back over here, that makes it a negative minus 2.3, so you need to remember that if you possibly can. Okay, the voltage gain to be expected in this circuit. Input resistor is 1,800 ohms, and the feedback resistor is 68 k ohms. So 68,000 divided by 1,800 is going to be approximately 38. I believe it's 37. Yeah, 37.777 rounds off to 38. Okay. And then this one, same thing again. What's the gain? Input resistor of 3,300 ohms, feedback resistor 47,000 ohms, so 47,000 divided by 3,300 is going to be approximately 14. Again, you can divide that out if you want on your calculator, or if you can remember, of course, that's okay too. 14 is the closest answer. What's meant by the term op-amp input offset voltage? Boy, that's a mouthful, isn't it? You remember there was an inverting and a non-inverting input. The differential input voltage is needed to bring the open loop output voltage to zero. So we're saying there the differential voltage, the voltage between the inputs, the two inputs, whatever that voltage happens to be that would give us an output voltage of zero, that is the op-amp input offset voltage. What is the typical input impedance of an op-amp? You remember we said the op-amps have a high input, a low output impedance, so this one is very high. Likewise, the output impedance is very low. Okay. What absorbs the energy from light falling onto a photovoltaic cell? So we're talking about photocells just a little bit. The protons come into the solar cell, and it activates the electrons. It makes them move a little bit, which in essence produces current. So the electrons produce that light absorb the light that comes in. What happens to a photoconductive material? A photoconductive is a little bit different from a photo or an electric generating type cell. Photoconductive means it changes as the light shines on it. So when you shine a light on a photoconductor, its resistance decreases by a predetermined amount. You can actually do some calculations with that if it were necessary. Those are the things that are used to control light dimmers, things like that, to turn lights on at night and so forth, are done with photoconductive material or phototransistors. What is the most common configuration of an optoisolator or optocoupler? Same thing, really. For one of those to work, we have on its input an LED or a light source. We put a voltage in on the light source. That light then shines on internal to the little device, shines onto a phototransistor. You'll remember the phototransistor decreases its resistance or turns on when it sees light. And so it will act like basically a relay, which gives you complete isolation between input and output. But the LED and the phototransistor work together. The LED lights up, the phototransistor turns on to activate the circuit that's hooked to the output across the phototransistor. So LED, phototransistor. A little circuit diagram for one of those. You see the LED there shining across to the phototransistor. That's what it actually looks like on a schematic. Well, our optoisolators are often used in conjunction with solid-state circuits that control 120-volt AC circuits. You remember we said one of the great advantages of this thing is isolation, and that's the primary reason. It isolates between the inputs and the outputs. Which of the following describes an optical shaft encoder? An optical shaft encoder is simply a rotary wheel of some sort with little notches or slots cut into it, and a light source on one side of the wheel and a phototransistor on the other side of the wheel. The phototransistor senses the light pulses that come through as the wheel rotates. So, which will describe that? A device that detects rotation by interrupting the light source with a patterned wheel. Patterned meaning it has a pattern of some sort, usually little notches or little holes in it for the light to pass through. And there's a pictorial of it. If you want to look at it that way, you kind of see what we're talking about. And then on the left of that little picture there, you see the rotating shaft with the interrupter disc, as it's called, has the little slots cut in it for the light to go through. As it rotates, that beam of light out of the LED light source is interrupted uninterrupted, and then shines through again on the next slot, and the photodetector detects that and counts the revolutions as the shaft turns. Can have some fancier things added to it. The one on the right there has a reference point, which lets the system know every time that it goes through zero, the wheel goes through zero, so it knows where it is. It can also determine which direction it's going by the other slots that's there. A lot of things you can do with that if you get fancy. Okay, photovoltaic effect. What is that? Converting light into electrical energy. That's where we shine the light into a substance that will produce current. It activates the electrons and generates electrical energy, light to electrical energy. What is the efficiency of a photovoltaic cell? Pretty much what you think. It's a measure of how much electricity is generated according to the amount of light that hits it. It's a relative fraction of the light that's converted to current. How is battery operating time calculated? You'll recall that our batteries are rated in amp hours normally. You have a 20 amp hour lithium ion battery, for example, or a 25 amp hour, or some of the big honkers out there, 100 amp hour batteries that are out there. The bigger that number, the bigger the battery, and the longer it will last us, of course. But what does that really mean? It means that the capacity in amp hours is divided by average current. So if we have a 20 amp hour battery, it could deliver 1 amp of current for 20 hours. That's the idea behind that particular thing. Now, as we'll see in the next slide, average current is something you have to consider. Well, on our radios, when we're receiving, we're not using very much current. When we transmit, of course, though, we use a lot more current. So we average all of that out to get that average that we talked about. So a little note there at the bottom, a 20 amp hour battery theoretically can deliver 1 amp for 20 hours, or 20 amps for 1 hour, or 10 amps for 2 hours. You get the idea behind what we're talking about for that. What's the purpose of an inverter connected to a solar panel output? Well, that solar output is DC, and we need to have AC coming out to do other things like power our appliances, or if we have a home solar panel system, we want to sell that extra AC back to the power company. So we have to convert the DC to AC, and that's the whole reason we have the inverter. Convert DC to AC. Okay. Which of these materials is most commonly used to create photoconductive devices? That's the crystalline semiconductor. Crystals, if you please, actually crystals of silicon, because it's cheap, quite frankly. What is the approximate open circuit voltage produced by a fully illuminated silicon photovoltaic cell? One exposed to direct light is about a 0.5 volt. That's just a good general rule of thumb. We get about 0.5 volts. So in order to get something that's workable, we would put a bunch of those cells in series. That would give us maybe our 12 volts, for example, if we put a bunch in series to do that. But the current would still be very low, so we'll take another series like that and parallel it. So we have both series and parallel cells to produce an adequate voltage rating and an adequate current rating. But the key they're looking for here is a single cell has 0.5 volts as its output. Most common material used in power generating photovoltaic cells, silicone. Not because it's the best, but because it's the cheapest and it has a long lifespan. It stands up well over time out in the sunlight. And that's the end of that one. Now, that was quick, wasn't it? Let me close that one out, stop the sharing, and we will go on to the next one. Without any big hesitation, let's jump into the next one. Let me go back to share again, and we'll go into chapter 14, test gear. Come on, test gear. Up you go. All right, there we go. We got it. Talking a little bit about test gear. All right, testing. There are not a whole lot of questions here, but so we'll just go right along, go through this one. I think we'll be fine with that. Which of the following parameters does a spectrum analyzer display on the vertical and the horizontal axis? We will compare a spectrum analyzer to an oscilloscope in several different places. The spectrum analyzer on its vertical axis, or the y-axis, delivers the amplitude of the signal that we're looking at. The horizontal axis, however, represents the frequency that we're looking at. So we might program our spectrum analyzer to show us, for example, the 40-meter band. So we tell it to show us from 7 megahertz to 7.3 megahertz across the horizontal axis. Then any signals that show up in that particular frequency span, we would be able then to see how big they are or what their magnitude is, how strong those signals are. So we would see the main signal we're looking for from our transmitter, for example, and we might see any spurs that pop up that we didn't want along with that would pop up in that same frequency span. So a spectrum analyzer on its vertical and horizontal axis shows the amplitude of the signal on the vertical and the frequency on the horizontal. And there's a picture of one. Unfortunately, it doesn't have the scales labeled very well, but going from left to right on that display is the frequency range that we're looking at. And I don't believe we're able to actually read what that frequency is set for. At any rate, the amplitude of the signals that it sees are shown vertically. There's one big spike there toward the right, just a little bit, that goes way up there. So we're seeing a main signal probably and some spurious signals to the left and to the right of it. Typical display from a spectrum analyzer. Which of the following test instruments is used to display spurious signals and/or intermodulation distortion products generated by a single sideband transmitter? Of course, we just talked about that and basically talked it into the ground. That's the spectrum analyzer. Which of the following methods measures intermodulation distortion for a single sideband transmitter? To test a single sideband transmitter, we inject into it 2 audio frequency signals. And be sure you note that we're talking AF signals, not RF signals, as the answers show. So we have 2 answers that deal with AF. We want to put in 2 audio frequency signals that are not harmonically related to one another. For example, we would not want to put in a 500 hertz signal and a 1,000 hertz signal, because that would be the second harmonic of 500 hertz. They have to be non-related, i.e. 500 hertz and 700 hertz, for example. And then we would look at the output on the spectrum analyzer, and we should be able to see a nice clean signal without a lot of garbage being generated on either side of it. So we modulate the transmitter using 2 audio frequency signals that are not harmonically related, and we see that on the spectrum analyzer. Standard test for single sideband transmitters. What is the significance of voltmeter sensitivity expressed in ohms per volt? When you buy a voltmeter or a multimeter, the voltmeter portion of it or the meter portion of it will generally give you an ohms per volt rating. Usually it'll be like 1 mega ohm per volt or 5 mega ohm, 10 mega ohms per volt, or it could even be more, but generally it's somewhere down in there. That sensitivity rating tells us how much that meter will load down a circuit that's under test. For example, if it only had a 10 ohm sensitivity, and we put a 10 ohm resistor across a 10 ohm resistor in a circuit to measure its voltage, we've just created a 5 ohm resistance there. It would really mess up the circuit that we're trying to measure. But if we put a mega ohm resistance across that 10 ohm resistor, it's insignificant. So it would not load down the circuit. So that's why the voltmeter sensitivity is so important. What's the significance of it? Well, a full scale reading of the voltmeter multiplied by the ohms per volt rating gives you the total input impedance of the voltmeter. So if we're looking at the 10 volt scale and we have a 1 mega ohm per volt, then we would have a 10 mega ohm resistance showing up at the probe that would go across whatever the load is that we're measuring for that voltage. So that would be very, very good. Okay. How much power is being absorbed by the load when a directional power meter connected between the transmitter and a terminating load, that terminating load could be an antenna, could be a dummy load, reads 100 watts forward power, 25 watts reflected power. So we're sending out 100 watts from our transmitter to, let's say it's an antenna, and we're getting 25 watts reflected back to us. And that's a picture of an old Collins meter there that measures forward and reflected power. You notice it has 2 scales, 200 in 2,000 watts. So in this case, we would use the 200 watt scale because we're working with a 100 watt transmitter. We would put it in the forward mode at 200 watts, read that, and we would see that it's reading 100 watts going out. Then we would flip the switch to the 200 watt reflected and see we have 25 watts being reflected. In other words, only 75 watts of what we sent to that antenna is actually getting there. 25 watts is being reflected back to us. So the answer, of course, then is 75 watts. 100 minus the 25 watts. Okay, a lot of discussion, says what we just said. Which of the following can be measured with an antenna analyzer? And there's a picture of an old MFJ, and I believe it was this one, the MFJ 269, that had a tremendous amount of capabilities. Would just measure just about anything that you can possibly imagine. And that's the case with this one, and that's the answer they're looking for. Velocity factor, which is how fast the signal travels down the cable, as opposed to how fast that same signal will travel in open space. The length of the cable, how long it is, the resonant frequency of a tuned circuit, such as maybe if you've created a onion or a ballon or something like that, you can check how well it responds. Just all kinds of things you can do with one of those antenna analyzers. Now, not all antenna analyzers can do that. I have a diamond. It measures the SWR and it measures the resistance, but it does not measure a lot of those other things like velocity factor, cable length. It just doesn't. It's not part of its capability to do that. But the answer they're looking for here for this particular one is a good antenna analyzer will do all of those things for us. Okay, and they mentioned here the network vector analyzer. We'll talk more about that. The Nano VNA is a very popular instrument, very inexpensive nowadays, so it's a good instrument to know something about. We'll talk about that more here in just a moment. Get a sip there. Thank you. Thank you for the pause. Which of the following limits the highest frequency signal that can be accurately displayed on a digital oscilloscope? Notice the word digital, not analog. The digital oscilloscope. The digital oscilloscope's frequency that it can handle is determined by how often it samples the incoming signal. The more samples per second, the more resolution you will get on the display of the digital oscilloscope. So that leads us to that answer, the sampling rate of the A to D converter. So that signal that's coming in is going to be sampled by an A to D converter. The more samples it has of that signal, the better the presentation will be on the oscilloscope. There's a rule of thumb that goes with that. You need, for this particular thing, you would need 2 samples per second to get the highest frequency. So if you're looking at a 100 megahertz analog signal, you'd have to have at least a 2 million samples per second just to get a bare basic representation. You really need more than that to give a good representation. 4 would give you a fairly good representation of the signal. 2 would be pretty pitiful. So, but anyway, of course, the price goes up on scopes as that analog to digital converter increases in what it can handle. You can get some little oscilloscopes now through Amazon and various other places down in the $50, $75 range that generally will measure a signal up to maybe 20 megahertz, 25 megahertz. But when you get on up there where you want to measure 100 megahertz or better, then the price goes up a lot. And you're often looking at prices approaching $1,000 when we get up that high frequency in order to handle that high frequency. Which of the following is good practice using an oscilloscope probe? So our oscilloscope probe has a little point or a little tip on the end of it. It has a short ground lead that's attached to it that we always attach to the chassis or to a good ground in order not to have reflected waves and other garbage show up that we don't want. But we need to keep that ground connection as short as possible, which means we want to minimize its length, i.e. the ground lead that comes from most oscilloscope probes is about 6 inches. You would not want to extend that with a jumper wire or something like that, so you have a 3-foot ground lead. It would pick up all kinds of extraneous noise if you did that. Minimize the length of the probe's ground connection. Okay, how do we compensate the oscilloscope probe so that it reads correctly? We're looking at wave shapes now on the oscilloscope, obviously. And when that probe comes out of the package initially, it's uncalibrated or it's not adjusted. And if we looked at a nice square wave signal, it might not look very square. It might look kind of crazy. So the manufacturer provides a little trimmer capacitor, a low value capacitor that's inside the probe that you can adjust to give you the best presentation on the oscilloscope screen. The way we do that, the oscilloscope provides a square wave that we look at, and then the probe is adjusted to the horizontal portions of the wave are as flat as possible or as square as possible. A picture of that would be like this. The input waveform that the scope generates for us to use for calibration would look like that nice required waveform display at the top on the right there, nice square clean waveform. And the oscilloscope generates this. Usually it's 1 kilohertz. And then the probe, as you see the picture on the left, has that little trimmer cap on it. And we would touch the tip of the probe to that wherever that 1 kilohertz signal is on the oscilloscope, adjust the trimmer capacitor to get as square a display as possible. Insufficient compensation you see in the middle, and too much when you start to get the spikes on the square wave at the bottom of that picture on the right. So that's just a little pictorial of what we're talking about. We need to adjust the trimmer to give us a nice square or flat-topped square wave. What is the effect of aliasing on a digital scope? Now here we're going back and forth. On a digital oscilloscope when displaying the waveform. If everything is not adjusted correctly, the ground lead is too long, there's half a dozen other reasons that can come up. You get a false, jittery, low-frequency version of the waveform. In other words, you get a garbage display, which they call false, jittery, low frequency. Looks something like this. Probably the signal they were trying to look at would be that tallest of the peaks that you see there on that display. But generally, as they say, your instruction manual will tell you that. Don't count on it. Just change frequencies, try a few different things in order to get rid of the extra garbage. So you get a solid display. Which of the following can be used to determine the Q of a series tuned circuit? You remember Q and wavelength are related to each other. So if we want to increase the Q, we would narrow, not wavelength, the pass band. And if we want to increase the Q, we would narrow the pass band. And that's essentially what we're talking about here. So determine the Q of a series turn circuit, the bandwidth, that's the word I was looking for. With the bandwidth of the circuit's frequency response would help us to determine that. We increase the bandwidth, we lower the Q, we decrease the bandwidth, and we increase the Q. That's a standard thing that many questions are related to on this test, of course. The higher the Q, the narrower the bandwidth. Okay, the nano VNA. Now we finally are getting down to this. Which of the following can be measured by a two-port vector network analyzer, or the VNA, the popular little instrument that's out there? And by the way, I just bought one of these nano VNAs. I bought the one that goes to 3 gigahertz, which is pretty high, really pretty good frequency range. It was $125 on Amazon, and it just do about everything but wash dishes, it seems like. I picked this particular picture, though, because you can see the channel 1, channel 0. Sometimes it'll be labeled a little different from that, but note there are two connectors on the left side of that thing for inputs and outputs. So it says, what can we measure with a two-port vector network analyzer? We would send the signal out on one port, check the signal coming back in on the other port. So what can we measure with one of these little guys right here? A filter frequency response, for example. It doesn't look at pulse rise, time, or forward, but doesn't measure power, doesn't do phase noise, but it will do a frequency response. That is probably a filter that we see that they're working with, and since they have cables on both connectors, that means they're putting a signal out on one connector, going through the filter, and looking at the signal coming back in on the other channel. That's probably what that is. That's my guess anyway. You notice on the picture at the bottom of it, have a start frequency of 5 megahertz, a stop frequency of 10 megahertz, giving it a total span of 5 megahertz that it's looking at right there. And then a dip right almost in the middle of that particular a set of frequencies that they have there. Okay, anyway, which can be measured with a two-port VNA, a filter frequency response. Okay, which trigger mode is most effective when using an O-scope? We're back to O-scopes again, and this doesn't matter whether it's digital or analog for the O-scope. Which trigger mode is most effective to measure a linear power supply's output ripple? You remember, linear power supply means we're talking about using a transformer to convert the 110 volt AC down to 12 volts or some multiple thereof. And then we go through a rectification process to convert that AC to DC. And then we have big filter capacitors to try to filter out the ripple. However, there will always be a little bit of ripple related to the line coming in. So we set the O-scope to sync using the line input, that is, sync to the AC line frequency, in order to be able to see the output ripple and observe that output ripple on the O-scope. So which trigger mode do we use? We use the line trigger in order to observe output, ripple output on a linear power supply. If it were a switching power supply, it would be using much higher frequencies, and the line would not work for that, for a switching power supply. What do the subscripts on the S parameters represent? And what they don't say here, we're talking about the nano VNA here at this point, or any vector network analyzer for that matter. We have two ports. What do the ports represent? Well, they're telling us how we're going to measure things, which ports the measurement's going to be made. Normally, you'll see those S parameters as S11 or S21. You also have S12 and S22. The nano VNA only has S11 and S21. But anyway, the ports at which the measurements are made. And another picture of one you see here again, port 1, port 2 as it's labeled this time. S11 is related to port 1, S21 related to port 2. So that notation that's there, that's just a way of saying what we're going to do. The first number after the S says, where are we going to be looking for that signal? Which port's going to be looking for our return signal? And the second digit tells us which port is going to supply the source signal for that. So an S11 means we're going to send the signal out on port 1 and look for a return on port 1. If we're going through a filter or something like that, we might send the signal out on port 2 and look at the return on port 1. And that's just an example of what we're talking about with the S notations. Which S parameter is equivalent to forward gain? Be the S21. To measure gain, you have to use two ports. You have to put a signal in and measure the gain of that circuit coming out, meaning you have to use two ports, which requires the S21, which indicates we're using two ports. Two meaning we're using port 2 as well as port 1. Okay. Which S parameter represents the input port return loss or reflected coefficient equivalent to VSWR? In other words, we're measuring an antenna here, the voltage standing wave ratio for an antenna. We would only be using one port, which would be S11, the first port. Signal's going out, looking for a return coming back in. So we're sending out and measuring on the same port. S11 indicates it's a one-port network. We're just using one port, send the signal out on that same port, and check its return on the same port. What three test loads are used to calibrate an RF vector network analyzer? When you buy the nano VNA, you will get these three test loads that you need. You'll get little connectors that connect right onto the nano VNA itself, or to your cables if you have cables attached to it. You'll have a 50 ohm load, a calibrated 50 ohm load. You will have a little connector that has a short circuit. That means the center pin is shorted right to the shell. And then you'll have another one that has no pin in it at all. It's totally open circuit. And we use those three adapters to calibrate out any spurious information that the VNA might pick up from the length of the cable or dirtiness in a connector or something like that. It'll basically zero out those errors so that what the measurement we get is accurate. So the three loads that we use are going to be a short circuit, an open circuit, and a 50 ohm load, and those are normally supplied with your nano VNA. Okay, and we said that already. Which of the following can be measured with a vector network analyzer? What do you guess on one like that? All of it. These we can do. Input impedance, output impedance, and the reflection coefficient. We can measure all of those by doing different things with the vector network analyzer. All of the above. What is described by the constellation diagram of a QAM or QPSK signal? Okay, those are modulation techniques on a signal. A constellation diagram refers to the fact that we would look into the heavens and we see a constellation, which is a pattern of the stars that represents something in our imagination. However, for this, it represents a pattern that indicates how effective the QAM or QPSK signal is, how clean it is, if you please. So what does it represent? Possible phase and amplitude states for each of the symbols. And for a 4 QAM, you get 4 dots. For 16 QPSK, you get 16. And fortunately, I have a picture of that coming up next. So phase and amplitude states for the symbols. And it looks something like this. 16 QAM, for example, is using 16 different tones, and you get a dot for each one as it's displayed there. If those dots are out of alignment, or if they're blurred, or if they're just totally messed up, that means your signal is not good. It should be a nice, clean display as shown there. And there's even a 64 QAM using 64 tones. So it just gives you an idea of what we're talking about. Hey, we're at the end of that one again. We are doing good. All right, let me kill that one. And okay. And we have been going a little over 30 minutes. So with that, we're now going to make the transition into antennas. Fortunately or unfortunately, depending how you look at it, there are about 63, I believe 62, 63 questions on antennas. So quite a bit on that. So it'll take a little bit longer to get through that one, but it's also good information at the same time. So let me share that slide presentation. And go full screen. And there we go. Okay. Antennas, here we go. Yeah, Birdie's out there warming their feet on it. Kitty Cat's warming himself on the amplifier, and all is cool. Okay, let's talk antennas, and here we go. And we're actually going to take about 25 or 30 of the questions. I don't remember exactly where we stop on this one, but we'll go through until it's time to stop. What is the term describing total radiated power takes into account all of the gains and losses? So when we transmit 100 watts, how much is actually going to arrive at the antenna? We would take into consideration all the losses. If we have an antenna tuner, if we have a long coax run, if we're using a balun at the other end, various other things that might get in the way that would give us a loss. Then if we have a gain antenna, an antenna that gives us some gain, we would add all those things together, and whatever that number is that's left would give us the total gain, or it could even be a loss of what's going in if we don't have a gain antenna, for example. So the term describing total radiated power, accounting for everything, is the effective radiated power. Effectively, how much power is going out. Effective radiated power is also of concern with the FCC, you might recall. They want us to check our effective radiated power in relation to how close we are to our antenna to make sure that we don't radiate ourselves with a bad amount of RF. Effective radiated power, how much is actually being sent out into the ether. Okay. Which of the following factors affect the feed point impedance of an antenna? Feed point impedance is that natural impedance of the antenna at the point where we attach our feed line, whatever that feed line happens to be. And one of the main factors that will affect its impedance is its height above the ground. How high is the antenna off the ground? That's especially true for wire antennas. In particular for wire antennas. How high is it off the ground affects the feed point impedance. Okay. Antenna efficiency is radiation resistance divided by total resistance. I don't know an easy way to remember that one. That's one we just pretty much have to commit to memory. Radiation resistance divided by total resistance. Which of the following improves the efficiency of a ground-mounted quarter wave vertical? ground-mounted quarter wave vertical. Ground-mounted means that antenna is mounted at the ground level, i.e. we've driven a spike into the ground and our antenna is mounted on that. Or if it's a real big antenna, we put some concrete into the ground with a tilt mechanism so we can tilt the antenna over if need be. At any rate, the bottom of the antenna is basically at ground level. So if we want that antenna to be more efficient, and in many cases it's actually required by the antenna manufacturer, we have to put some radials in the ground or on the ground radiating out from the base of that antenna. Basically, the antenna is a quarter wave vertical, so in order to get the other quarter wave to give us a half wave effective antenna, the ground radial system makes up the other half of the antenna, if you please, to give us a full half wave antenna. That's the essence of what we're trying to accomplish. That's a picture of one. A guy there has really gotten serious about running his, oh my goodness, running his ground radials out there. He's got a whole bunch of them running out in all directions. Normally, those radials would be a quarter wavelength in length. If you're doing a multi-band antenna, you would have different radials at different lengths, depending on the bands that your antenna would handle. Good ground radial signal will give your signal more punch. That's an understatement. Which of the following determines ground losses for a ground-mounted vertical antenna operating at HF? Again, ground-mounted is the key there. It's attached to the ground, if you please. If the soil is damp and more conductive, it will help it. If the soil is really dry, it will hinder it. Soil conductivity. How well does the soil conduct electricity? It depends a lot on how wet the soil is, how damp it is, and the type of soil, of course. How is the far-field elevation pattern of a vertically polarized antenna affected by being mounted over seawater as opposed to being mounted over soil? How does that elevation pattern go out from the antenna? If we move from the ground out to a boat, perhaps, and we're over seawater, when we do that, the radiation at low angles increases. The radiation angle goes up just a little bit. Actually gives us a much greater ground system, if you please, with the salt water because it's so conductive. And an antenna over salt water normally is quite efficient. At any rate, the answer they're looking for, radiation at low angles increases. And that's a picture of that, showing some lower angles there. The blue one showing a lower radiation angle, which means it travels further on the first hop. Now, of course, these signals can bounce back and forth on the ionosphere. They don't necessarily just make one hop, depending on time of day and so forth. So we mount it over salt water. We get longer communications distances. What is the primary function of an external earth connection or a ground rod? And I had a lot of thoughts about that, but we have to go with what they're looking for in their answer. And their answer is lightning charge dissipation. That's their primary concern. We put the ground rod out there by our antenna in order to discharge things that result from lightning. Now, we know that if our antenna takes a direct hit from the lightning, it doesn't matter what you have out there. It's going to be melted. The coax is going to be melted. And anything within a block radius of that particular antenna is probably going to get melted or at least smoked as well. But we're talking about here just some of the charged things, i.e. You get a lightning strike that's a quarter of a mile away. You'll get a lot of static electricity that would hit your antenna. So the grounding system would help take care of that static and not allow it to go into your radio or into your system in your shack. There's a picture of a lightning arrestor. We would normally put that lightning arrestor in the coax line. That little terminal on the top of that thing is where a ground wire would attach. The ground wire would go down, would need to be minimum bends. If you have to bend the wire, you make it a wide radius bend, i.e. no sharp corner bends, and take that down to a ground rod. And that little device there, if it senses static charges, whatever, it will siphon those off and take it to ground instead of letting it go to your equipment. At the same time, it will let the RF signal, though, pass right on through it unhindered. What type of radiation pattern is created by a quarter wavelength vertical two quarter wavelength verticals rather, spaced a half wavelength apart, fed 180 degrees out of phase. Now, there are three questions in a row here, and the way we're looking at it right now that talk about this. So hopefully the way that's laid out and the diagram that we've been provided will help us to put this together in a way that will help us to understand it. Two quarter wave verticals, half wavelength apart, fed 180 degrees out of phase, gives a figure 8 pattern along the axis or along the length of the distance between the two antennas. And that's shown there on the left on diagram A. There are two antennas together. The radiation pattern would look something like that. It goes along the axis or the distance between the two antennas, i.e. the radiation is going from number 1 to the left and from number 2 to the right. So that's the radiation pattern for the antenna. Now, the next question is going to use another one of those. Radiation pattern for two quarter wavelength vertical antennas spaced a quarter wavelength apart, fed 90 degrees out of phase. And again, I'm guessing this is one of those where we just have to memorize the answer in order to make it come out. It's going to give us a cardioid response. Now, you might associate cardioid with microphones. That's one of the specifications of a microphone oftentimes. It has a cardioid pickup pattern, which means basically it picks up sound more in one direction than it does in the other. So that's the pattern we're looking at here. Two vertical antennas, quarter wavelength apart, 90 degrees out of phase, gives us that pattern that's in the middle of that diagram. So we basically created a directional pattern here with most of the signal going from number 1 going toward number 2 and out to the sides rather than going backward to the back. AM broadcast band radio stations often use that. If they have a clear channel station, they'll set up two vertical antennas like that in order to direct their signal in the direction that they've been licensed to send it. What type of radiation pattern is created by two quarter wavelength vertical antennas, separated by a half wavelength again, but this time fed in phase? Okay, back to the figure 8 again, but the other one broadside to the axis, that is side to side. And that's the third pattern over on the end there. The number 1, the number 2 antennas you see are radiating up and the way that figure is laid out, they're radiating equally up and down rather than going in one direction or the other specifically. So anyway, again, I don't know an easy way to remember that other than just to memorize which answer goes with which question. What happens to the radiation pattern of an unterminated long wire antenna as the wire length is increased? So we take a long wire antenna and we keep making that antenna long, making that wire longer. As it goes out, we create lobes or little areas that send the signal in a particular direction, or if it's a receiving antenna, will receive from one particular direction. As we add length to that, we will add more lobes to it, and they will align with the axis of the antenna or the direction the antenna is pointing, up to a point till we reach the point of diminishing returns. We can't get too long where it no longer works like that. But most of us don't have the real estate to do that long an antenna anyway. But anyway, the answer is additional lobes form with major lobes increasingly aligned with the axis of the antenna, making it more and more directional as it gets longer. Okay. A folded dipole, as you might expect, means it's a dipole antenna with a second dipole in parallel to it. That's basically what we're talking about here. So what is a folded dipole? A half-wave dipole with an additional parallel wire or antenna connecting its two ends, the two opposite ends of that antenna. We have a picture of that next. It shows a folded dipole there, a half wavelength long, and then another half wavelength of wire below that connected on either end of the antenna together, and then going into our feed line, giving us two half waves in parallel. A lot of people will build this using the old 300 ohm twin lead that we used to use for TV signals, TV sets. You measure out that thing, the length of the length of a half wave, and you already have the two wires. You solder the two ends of the wires together, clip one of the wires right smack in the middle, attach your feed line to that, and you at that point have a folded dipole. Okay. What is the approximate feed point impedance at the center of a two-wire half-wave folded dipole. We talked about making this out of 300 ohm twin lead, the old TV antenna wire. So that hopefully that 300 ohms will help you to remember that. The center impedance is approximately 300 ohms. Remember, the TV twin lead looks something like that picture there. It's just two wires with insulation around them with a little plastic part in the middle there that keeps the spacing equal along the distance of the wire. Old TV twin lead. What is the purpose of feeding an off-center fed dipole? So we're now moving to off-center feds. Why do we feed the off-center fed dipole between the center and one of its ends instead of feeding it at the midpoint as we would with a standard dipole? Well, the off-center fed dipole has some neat characteristics. It can do a lot of different things. One of its characteristics is it can radiate both odd and even harmonics of a signal coming in. So it will create similar feed point impedances on multiple bands, which is the characteristic of the OFCD antenna. It's a multi-brand antenna by its nature because of this off-center fed feeding mechanism. Gives a similar feed point impedance on many different bands. So you may have one antenna up that will cover everything from 80 meters down through 6 meters, for example. And it's all done by where you place that off-center fed feed point. Okay. G5RV antenna. That was an antenna that was invented by a guy in Great Britain. It's kind of an interesting antenna. It's a dipole type antenna, but it's fed with ladder line, open wire ladder line. That's the characteristic of it. That's just the way it's made. So it's a center fed antenna that has an open wire line connected or ladder line connected to a balun, and then the balun is then connected to your coax line that goes into your radio. That open wire line, that ladder line, has to be a specific length in order for it to work correctly. So wire antenna, center fed, specific length of open wire line connected to a balun and a coaxial feed line, looks something like that. So you see the dipole antenna is 90 feet long there. And then you have that section of ladder line, which is 40 feet, 1.5 inches. You see that's very specific on how long it needs to be. Goes into a balun, which will let us attach our regular coax to it at that point. The balun then will help to match, but primarily it will keep any radiation from occurring out of our coax line. Resonates on a lot of different bands, as you can see, and then some other bands if you use a tuner with it as well. So G5RV is a fairly popular antenna, at least very popular, maybe not quite as much now. You can buy one commercially from just about any place that sells amateur radio supplies. Okay. And did I just miss one? No, I didn't. Okay, that's still talking about that. All right, moving on. Excuse me. Which of the following describes a ZEP antenna? Where do we get the name ZEP for an antenna, pray tell? It comes back from the old days of the Zeppelin. You remember the Zeppelin was essentially a balloon with engines and motors attached with propellers and all that good stuff to make it go through the sky and give us a form of air transportation. In order for it to communicate with the ground, it would trail an antenna out from the bottom out behind it. So it would be fed, that antenna then would be fed from one end. So guess what that makes it into? It makes it into an end-fed half-wave dipole as a ZEP antenna. Okay, I mentioned here, it comes from the old Zeppelin airships. They use a quarter wave ladder line Q section to match it to their radios. The J-pole antenna we often use now on VHF, UHF is a form actually of a ZEP antenna. Okay, now then, we get to an extended double ZEP. EDZ as it's sometimes termed, what describes an extended double ZEP antenna. This one is a weird one. It is 1 1/4 wavelength long, 1.25 wavelength dipole. Now that's really kind of strange, isn't it? But it really has a reason for that. If you divide that 1 1/4 length dipole into two pieces, you have two 5/8 wavelength quarter wavers. A lot of the antennas that we use on our mobiles are 5/8 wavelength because it inherently gives us some gain. So by putting these two 5/8 wavelengths together as the dipole, we actually get some gain from it. Call it extended double zip, 1.25 wavelengths long. Has about 3 dB of gain, which is not all bad, not all bad at all. A little bit over 50 ohms, so it needs some kind of matching to make it work like it's supposed to. An isotropic radiator. Whew, look out. Watch out for the word hypothetical. That's where we start with isotropic radiators. It's a hypothetical antenna. In other words, it doesn't really exist. It's a lossless antenna, which also doesn't exist. There's no such thing. It's a hypothetical lossless antenna that will radiate equally in all directions, used as a reference antenna for measuring gain. So hypothetical is the key to that. Okay, a picture of that right there, just showing this hypothetical antenna radiating in every direction equally. Okay, what is the effective radiated power of a repeater station with 150 watts transmitted output power, 2 dB of feed line loss, 2.2 dB of duplexer loss, and a 7 dBd antenna gain? Now you notice we got dB, dB, and dBd. dBd means dB dipole. This is one of those specifications. Sometimes you'll see dBi, which means reference to an isotropic antenna. But for our purposes here, it doesn't matter. We're just going to add those things together and see what we come up with. So 2 plus 2.2 is 4.2 of loss, 7 dB of gain. 7 minus 4.2 is 3.8. A 3 dB gain would be a doubling, or 300 watts. So we don't quite have 3 dB, so it's going to be a little less than double. The closest answer to that then is going to be 286 watts. So we can kind of approximate that one and get the right answer. That one is fairly easy. Okay. Now, just try it again. We've got a 200 watt transmitter, 4 dB of feed line loss, 3 dB of duplexer loss, 0.8 of a dB of circulator loss, but a 10 dB antenna gain. So here we go again. 4 plus 3.2 plus the 8. Let's do the 3.2 plus the 0.8 is 4. 4 and 4 is 8 dB of loss, 10 dB gain. So we got 2 dB of gain overall. This one is tricky. 2 dB of gain. So it's going to be over 200 watts that we're putting out, but it's not going to be doubled. 317 and 300 are both close answers, but which is it? This is one you probably just need to remember, that it's 317 watts. Now, you can calculate that, do all kinds of things. If you had access to the lookup table, you can do a lookup table and find that 1.585 is the gain factor with the 2 dB. We don't have that, so it's easier if you can just remember the answer for that thing. Excuse me, and I just went the wrong way. I meant to go back. I'm sorry, I can't go. I'm having a hard time going back. So we're looking at 252 watts out of that thing. Just one of those things where you got to just calculate it and get the closest answer. That one, though, you might want to remember it. Okay, let's see here. What's the difference in radiated power between a lossless antenna with gain and an isotropic antenna driven by the same power? Now, first of all, what is a lossless antenna? It's theoretical, right? It's not a real antenna. The isotropic radiator, again, is a theoretical antenna. So we feed those with some kind of a signal. So they're asking, what's the difference? It doesn't matter. They're both theoretical antennas. We're driving them with 100 watts. They're both going to see 100 watts. It's not going to matter what the difference in radiated power is going to be. The power is there. They're not going to gain any power as such. Even a directional antenna, which gets shown as having, say, 3 dB gain, is not putting out or is not generating 300 watts of power. It's basically taking the power that would have gone in all the different directions and focusing it in one direction. So in this case, though, these are two theoretical antennas driven by the same power. They're going to be the same as far as their output power, their theoretical output power. They're the same. Okay, receiving directivity factor. I have to say, I don't know that I've ever run across this one before. Again, just one that's, I guess we have to just give it to memory. What is that? And if you can remember, it's the longest answer, that might help. Peak antenna gain compared to the average gain over the hemisphere around and above the antenna. Okay, got it. I really don't know how to even comment on that one. When dealing with receiving antennas, the overall gain isn't always the most important factor. Sometimes you can improve the receiver's signal to noise ratio by sacrificing some of the gain in this direction or directions from which unwanted noise arrives. The RDF of an antenna is generally a better indicator of a receiving antenna's effectiveness than gain alone. Receiving directivity factor, RDF, is defined as peak antenna gain compared to average gain over the entire hemisphere around and above the antenna. So hopefully you can remember it's the longest answer. Excuse me. I got to wet the throat just a moment. How much gain does an antenna have compared to a half wavelength dipole if it has 6 dB gain over isotropic? Okay, and we get into a little bit of math and playing games with this. We say that normally a dipole has 2.15 dB of gain over isotropic. So we subtract the 2.15 from 6, we come up with 3.85 is the actual gain for that thing. And that's another one. Just remember that 2.15 is the gain of a dipole over isotropic. Well, and that pretty much is a standard. Hopefully that will help you to remember that. 6 dB minus 2.15 gives 3.85 gain. The isotropic has a theoretical gain of 1, i.e. no gain, no at all. What happens as the Q of the antenna increases? The bandwidth is going to decrease. Remember that? Q goes up, bandwidth goes down, and vice versa. So as the Q increases, the bandwidth is going to decrease, give you a narrower band. That'll always be the case. What is the function of a loading coil in an electrically short antenna? And then an antenna like a vertical mobile antenna, for example, and we put a loading coil down at that antenna. The function of that is to resonate the antenna by canceling capacitive reactance. If it's short, it's going to be capacitive in its reactance. We put the coil in there to offset that. Okay. That shows a picture of one. You see that big old coil down at the base of that antenna. Tunes out the capacitive or nulls out the capacitive reactance. Which frequency band has the smallest first Fresnel zone? And this may be one with which you're not familiar. And honestly, I had to look this one up and read up on it just a little bit. The Fresnel zone. The answer to that is the largest number that's there, the 5.8 gigahertz. Now, the explanation is not too bad here. A Fresnel zone is the line of sight distance between 2 points. And generally, and when we're talking the high frequencies, we're talking line of sight for communications to work. But in that line of sight, there's a watermelon-shaped area around that line of sight line. If things intrude into that zone, it's called the Fresnel zone. If things like a tall building, as is shown there, intrude into that, it can attenuate or affect the signal between the 2 points. So that's the Fresnel zone. In this case, that highest frequency is the one that's most susceptible, and that was the answer that they were looking for. The 5.8 gigahertz has the shortest wavelength of all the examples, so it has the smallest zone because the wavelength is the shortest. Okay. What happens to SWR bandwidth when one or more loading coils are used to resonate an electrically short antenna? So again, we're adding coils to an antenna. Okay, what happens to its bandwidth? It's decreased. Okay, I don't know an easy way to say that, other than we're playing with the Q again. Decreasing resistance increases the Q, decreases the working SWR bandwidth. Why should antenna loading coils have a high ratio of reactance to resistance? In other words, we want to use fairly large wire so that they don't have a lot of resistance anyway. It makes them more efficient. Of course, that's generally the case. And that's a picture of one of those big loading coils. Sometimes you'll see this. People will use the Tar Heel antenna, which uses one of those great big coils like that on the bottom. And it helps to maximize the efficiency of that antenna. Bigger the coil, lower the losses. What is the most efficient location for a loading coil on an electrically short whip antenna? Where do you put the loading coil to make it most efficient? Put it near the center. Often you'll see it on the base because that's a little bit more stable at the base, but you can put it in the center. Oftentimes you'll see vertical antennas, mobile antennas in particular, with loading coils both the center and at the base. But in this case, the answer they're looking for is near the center for the most efficiency. And that shows that same antenna again. I don't know if that rod is wound with wire or not. It doesn't really, I can't really say. Anyway, that loading coil is toward the base. Advantage of top loading an electrically short HF antenna. Okay, remember electrically short means it's capacitive. So give improved radiation efficiency, make it radiate better if you put the coil at the top. There's a trade-off on anything we do, isn't it? That's just how that's how it works. Interesting comment there. It's easy to understand why the little 96-inch CB whip antenna with an automatic antenna tuner will not perform as well as a resonant center-loaded, helical-loaded, or top-loaded vertical antenna. In other words, one with a coil in it. The single whip just doesn't work out nearly as well. It's not as efficient as having the coil. How long is a Yagi's driven element? Oh boy. How do we deal with that? Okay. Let's see. Approximately how long is it? Is the Yagi's driven? Remember, Yagi has multiple elements on it. One element's driven. Behind it, you have a reflector. In front of it, you have directors. So it's going to be, normally it's going to start out at a half wavelength. It's basically a dipole, in other words. Half wavelength. Say feed point impedance of a typical 3-element Yagi between 25 and 35 ohms. So you have some kind of matching, and you'll see those in various types of matching devices. How does the radiation resistance of a base-fed whip antenna change below its radiation or resonant frequency? That's a mouthful. Radiation resistance decreases, and that's one we just have to remember. And we can play with the formulas if you want to. Probably easier just to remember that. Why do most 2-element Yagis with normal spacing have a reflector instead of a director? Now, 2-element Yagis are a little unusual, but you will see those at some of the greater greater wavelengths, like at 20 meters or something like that. And you'll see Yagis for that. And you may see 2 elements. Usually, when we're VHF, UHF, we'll see 3 or 5-element Yagis. Anyway, why do most 2-element Yagis with normal spacing between them have only a reflector and not a director? Because it gives you better gain. It directs the signal out as in the direction of that the radiating element is creating the signal, giving you a better signal, higher gain from it. Okay. And there's a picture of a Yagi antenna. The driven element shown there. You'll notice that the driven element, which is normally the half wavelength, the reflector is behind it is just a little bit longer. The directors that are in front that help to pull the signal toward the front are a little bit shorter. If you put more than that on there, they'll get increasingly short, or they'll become shorter as you go out toward the left side of that antenna, as it's shown there. There's all kinds of ways then that you can match that thing to get the 50 ohm impedance that you need for your coax cable. What's the purpose of making a Yagi's parasitic elements either longer or shorter than resonant? To control phase shift, to make the signal behave itself, you might say, but controlling phase shift by adjusting the spacing between the elements. What is the far field of an antenna? Oh boy, far field, region where the shape of the radiation pattern no longer varies with distance as it goes out. As the antenna gets longer, as the signal goes out, when it gets to the point where the radiation pattern no longer changes, that is the far field of an antenna. And we can play with that. Generally, the safe airway calculated MPE. We mentioned this earlier. That is the maximum possible exposure. That's where the total radiation comes into play. We want to measure that to make sure we don't have too much exposure to RF. What does the term ground gain mean? Signal, an increase in signal strength from ground reflections in the environment of an antenna. Ground reflection, ground gain, same thing. And I believe I need to stop right there. So let me double check where we are with this. We're a little about an hour into that. I believe we're where we need to stop. Yes, we are. Okay, so we're going to stop for that one. We will pick it up again at that point on the next session, which is, we said there's only one session remaining, and that'll be on the 25th of June. And then testing will be that following Saturday. One of our members has already tested. He went over to Louisville to the Hamfest over there last weekend and tested and came out and got 44 out of 50, which is a great passing score. Congratulations, Jerry. We're proud of you, and we're glad you're with us on this session. And we'll be looking forward to seeing you again in person here, probably field day, if not before. Have a great evening, everybody, and we will catch you on the next session. Good night, all.